In the last lesson, we talked about how to graph different types of piecewise functions, and we looked at the key features of them. In this video, we're going to be looking at additional types of functions. So we were sticking to just some basic polynomials, linear and quadratic. But now let's look at a few other functions that we might see in a piecewise function. These aren't all the ones. You could see literally any function in a piecewise function, but these are pretty typical ones. So a polynomial, just remember that a polynomial, that's a big umbrella term. So in a polynomial function, you have a linear function, which looks like this, because the degree is 1. You have a quadratic function, looks like this, the degree is 2. And then you have a cubic function, looks like this, that's degree is 3. Now we could keep going, but those are the most basic ones. So you have polynomial functions. You should be super familiar with those three, how they look. So when you see the graph of each of those, you can identify what they are. The next one that is used commonly is a square root function. Looks like this, like a swimmer's arm is a lot of times what it's referred to as. A rational function can come in a lot of different ways. The most basic rational function has like two pieces, I would say. And it looks something like this. It's approaching those asymptotes. An absolute value function, we should be familiar with the V shape that it has. And then an exponential function has that exponential curve. So first we just need to be familiar with recognizing which type of function exists and what their general shape is. So in order to graph piecewise function, the first thing we need to do is determine the parent function of one piece. So we start with the first piece. Don't look at them all at the same time. That can be overwhelming. The next thing we're going to do is determine the transformations. Where did it go from the parent function so that we can easily graph it? Did it go up? Did it go down? Determine the transformations. And then the next thing we want to do is graph for the specified or specific domain. So we're not going to graph on the entire domain of that function. It's just whatever the piecewise function says I'm supposed to graph at. And then the last step is just to repeat for each piece. So let's look at this first example. We're going to start with the equation of the function and try to graph it. And then we have a few key features to find from that. So piece 1 is a linear function. These 1, 2, 3s are the steps that I told you at the beginning here. So this is a linear function. And where did it go? Well, actually, it did 3 different things. So it went down 1, so down 1, and then, because the minus 1 on the outside, it reflected. So this function is a linear function. It's going to be going down. That's because of the negative there. And then the 2, the stretch, vertical stretch. The last thing is to graph it, and we have to look at the specific domain here. It's where x is less than or equal to 2. So we have to pay attention to that. That's right here. So let's first think about, this is a linear function, but it went down 1, right? And then it's going to reflect, so instead of going up 2 over 1, it's going to go down 2, and it's going down 2 and not just 1 because it was stretched. So down 2 runs a little bit off, but that's okay. It's down here at 5, I believe that is. And this is a linear, so it's supposed to be a straight line. Now this is a closed circle, and the reason this is a closed circle is because this says or equal to, right? Now let's look at the second piece. So the second piece is also linear. We know that because it's just x, right? There are 2 transformations that occurred. It went up 4, and it also reflected. See how there's a negative? So if we started at the origin and went up 4, and then it would, since it's reflected, we go down 1 over 1, down 1 over 1. So here, So was it 4, down 1, over 1? It would be an open circle. And I do just want to point out here that some of these can be pretty challenging, which is why I showed you how to use Desmos in the last video to check your work. So remember, this one was also going down, so. Okay. This is from x is greater than 2, which is why we have that open circle there, right? If it was a closed circle, then it would not be a function anymore. So because it just says greater than, open circle. Now, for some reason on my little worksheet, this didn't work out exactly as I had planned. It's on the next page. That's okay. So let's just do the domain first. The domain is your x values. Now, in this case, this goes all the way to the left and all the way to the right with no problems, right? So the domain is negative infinity to positive infinity. There is a jump here, right? But the value of x equals 2 is accounted for, so that's okay. The range is also negative infinity to positive infinity. So we have to be really careful when we talk about range because it goes up forever, which is great, and it goes down forever, which is great. But this is the kicker with piecewise functions, that every point in between is accounted for, and in this case it is. So every y value is accounted for by the use of these two functions. Every y value is accounted for. So domain and range, all real numbers. This function is increasing nowhere. So there is no point where this function is increasing because as we read left to right, it's decreasing on both of these intervals. So it is decreasing from negative infinity until we get to this point at 2, right? Now at 2, it's not technically doing anything, so we're just not going to include that. And then it continues to decrease all the way to infinity. The last thing I asked is this a continuous function? And the answer is no, it is not continuous because I cannot trace this entire thing without picking up my pencil. There is a jump from here to here. Okay, so this one gets a little crazy. There's some different functions here. So let's start with piece 1. So piece 1, we should be able to identify that as an exponential function. It is, and I'm going to abbreviate, exponential function. So what are the transformations that occurred on that exponential function? It's going to be reflected. Reflected. And I'm going to be specific here, over the x-axis. The reason I know that is because of the negative. Now, I only need to graph this from where x is less than negative 4. Now, this is something in particular, I'm going to have to use a different scale because my graph only goes to 4. So I'm going to use these as like 2, 4, 6. So just to keep that in mind. One thing that's helpful here is even though at negative 4, this is not included. So because it's not included, it's going to be an open circle. It's helpful to plug that in so that we know, like, where are we at on the function. So that's what I'm going to start off by doing. So I'm going to do negative 2, and then I'm going to plug in negative 4. Negative 2, well, the negative's on the outside. So 2 to the negative 4th, remember that flips the fraction. So this ends up being negative 1 over 2 to the 4th. And that's negative 1/16. So this is a really small number. So just understand that at negative 4, our function is at negative 1/16, so very, very small. Usually the function, because it has been reflected over the x-axis, that's why it looks like that. So this is really, the only piece that we get to see just looks like it's approaching the x-axis from this side. So this is an open circle, and I tried to do that at 1/16. That's really close. This is going to just approach this asymptote. There's not much fun to that exponential function because we kind of missed the curve part. But plugging those values in are helpful. Okay, so the next one is an absolute value function. Absolute value, I know that because it has the absolute value marks. So the only transformation that occurred here is another reflection over the x-axis. So reflected over the x-axis. So that means it was a V, right? But now it's a V like pointing down. So this is going to be closed. These circles are closed. From here, negative 4 to 0. Now, it's not going to look like a V in our case because we don't get to draw the other piece on the other side, the other part of the V, because our function was stopped at 0. This function was from -4 to 0. And the third piece is a quadratic. And I know that because there's a square. There's a quadratic. There are 2 transformations. It went up 4. Now, I want y'all to remember that this is the same as me saying -x squared plus 4, right? If I just change the order, and then this would be an outside number. So that brings us up 4. And then the other thing is another reflection over the x-axis. So reflected over the x. So that means this function is not going to be a u like facing up. It's going to be a u facing down. And we want this function when x is greater than 0. So let's try to draw this one. Now, usually we start at the origin, but this one went up 4. Now remember, I'm using these as like 2, 4, so this would be 4. Now this is an open circle. And the reason it is an open circle is because this is not included. X is not included in that particular part of the function. So instead of our quadratic facing up, this one was going down. So it looks something like that. You can always check your work in graphing, and I would suggest doing that by plugging in the piecewise function into Desmos and taking a look at that. So let's talk about the domain and the range. The domain, all real numbers exist here because there's no nothing not accounted for, right? From -infinity all the way to positive infinity, all of those numbers are accounted for. So now let's look at our range up and down. So we know the function goes down forever. It does not go up forever. So there is a piece that it's going to stop at, and it actually stops here. So the lowest value is -infinity, and then it goes up to the highest value of that 4. That 4 is not included because it is an open circle. Now, remember, and I went ahead and wrote this, you have to make sure that every value of y in between those is accounted for, and in this case, it is. So where is this function increasing? Well, if you take a look at the first piece, remember, this is kind of difficult to tell. It's not a constant function. This part is actually decreasing. So this portion is going down because as we go to the left, it's getting closer and closer to that x-axis as the horizontal asymptote. So that portion is decreasing. So from -infinity until we get to -4, that's decreasing. The next piece, this interval right here, is increasing. So that would be from -4 to 0. We're increasing. And then the last piece, my green portion, this is decreasing. So I would say union, and then from the point 0 to infinity. And remember, we're talking about the x-axis here. Is this function continuous? The answer here is no. It is not a continuous function because there are jumps here, right? I couldn't trace this entire graph without picking up my pencil, so it is not continuous. All right, last one. So there's 2 pieces to this piecewise function, and the first one is a rational function. We know it's rational because there is a x in the denominator, and so the transformation, there's only one transformation. It went right 4. And I know that it went right 4 because there's a -4 that's with the x. And remember, it's opposite of what you would think. So again, keep in mind that my scale here is going to be going up by 2's. -2, -4, -6. All right. So I know my function went right 4. And so at that particular point, this is going to be a vertical asymptote. That makes the denominator equal to 0 if we're just looking at this piece. And so we're never going to actually get to that. It's just going to look sort of like this. Right? So that is the nature of a rational function. Again, I know that actually graphing these can be super challenging. So remember that you have Desmos to kind of check that work. So this is only when x is less than or equal to 4. So if it was the entire thing, another piece of the function would be over here, but we don't include that. Don't write it. I hope you're not in, don't have pen. We don't put that portion, and the reason we don't is because we have a restricted domain. It's just when it's less than 4. Okay, so what happens when it's bigger than 4? Well, when it's bigger than 4, we have a constant function. Remember, a constant function is just a number, and it is a horizontal line. In this case, our horizontal line is going to be at -4. You could, I guess, say that it went down 4 from y equals 0, but when we draw this horizontal line, this needs to be an open circle. The reason that needs to be an open circle is because we have a restriction on the domain where x is just greater than 4. So let's look at the domain. So the domain of this function, all the way -infinity, we're good until we get to 4. Now 4 is not included in our domain, and the reason is because it says that it's in the first function, but can we plug 4 into that denominator? We certainly cannot, because it would give us 1/0, which is undefined. So it's everything except for 4. Now the range is my y values. So the lowest y value it goes, well, it's going down forever, so -infinity. And then it goes, it's including all these values, it goes until it gets over here. This is approaching an asymptote as well at 0. And so it never gets to 0 and never gets above 0. This function is actually never increasing. If we trace it from left to right, this is going down, and this is neither increasing nor decreasing, so there are no increasing portions of this function. It's going to be decreasing from -infinity until we get to 4. This piece, again, is not increasing or decreasing. Is this function continuous? The answer is no. There are functions that are continuous, just not these examples. Because in order to graph this, I would have to pick up my pencil.